All right, let's talk about getting our definition of derivative. All right, so to get the definition of derivative, we've got to get a definition for finding the slope of a tangent line. So if we have this, and we've got some function f, and we want to find the slope of the tangent line at point P, here's how we're going to get it. First, let's make up some coordinates for point P. We'll call its x-coordinate x. If we call its x-coordinate x, what would be a fairly logical name for its y-coordinate? F of x. Y, which we can call f of x. Okay. Then we have point Q over here. Now here's the way we're going to get the x-coordinate of Q. We started here at x, and then we went some distance that we're going to call delta x. Okay? So delta x, the Greek letter delta, the little triangle-looking thing, represents the change in x. So we change the x-coordinate by this small amount, okay, which we're calling delta x. So for instance, if delta x was 0.5, then the x-coordinate of Q would be x, because that's where we started here, plus 0.5. If delta x was 0.4, the x-coordinate of Q would be x, because, again, that's where we're starting, isn't it, with an x, plus 0.4. So the x-coordinate of Q is x, because that's where we started, the x-coordinate of P, plus delta x. So that's the x-coordinate of Q. All right? The y-coordinate of Q. Let's name it in a similar fashion to the way we named the y-coordinate of P. Since the x-coordinate of P was x, we called the y-coordinate f of x. If I knew the x-coordinate of P was 7, I could call the y-coordinate f of 7. So then look at Q. Its x-coordinate is x plus delta x, so its y-coordinate is f of x plus delta x. Okay? Everybody with me? Now, to get the slope of that secant line, line PQ, I can use the good old slope formula that you've known for a long time. Okay? And I can substitute in, all right, y2, the y-coordinate of our second point would be f of x plus delta x, minus y1. What are we going to put into this formula for y1? F of x divided by x2. What's the x-coordinate of the second point? X plus delta x minus x1. What's the x-coordinate of the first point? So then when we simplify this, we'll get f of x plus delta x minus f of x over, and then that x minus that x is 0, so over delta x. So that is the slope of the secant line. Now, the slope of the tangent line. Remember what we've talked about? We've talked about this a few times now. If we move Q closer to P, then the slope of that secant line, the new secant line, is closer to equaling the slope of that tangent line. I'll go ahead and sketch in the tangent line. There's the tangent line. It's got a slope, right? I don't know what it is, but it's got a slope. If I move Q closer to P, the slope of that new tangent line is a little bit closer to equaling the slope of the new secant line is a little bit closer to equaling the slope of the tangent line. Closer, 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 closer. It keeps getting closer, right? As I move Q closer to P. Now, as Q moves closer to P, what's happening to delta x? It's approaching 0. So instead of saying the limit as Q approaches P, how about saying we're finding the limit as delta x approaches 0? So the definition of the slope of the tangent line is that it equals the limit of this slope of the secant line as delta x approaches 0. Questions? All right, so that's the definition of the slope of a tangent line. We then decide, we, as if I'm Isaac Newton, we then decide that this is such an important concept that we're going to give it a special name. We're going to call it the derivative. So, f prime of x means the derivative of f of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And that's the definition of derivative. Okay? All right, so far so good? All right, now let's start doing something with this. You ready to? Hey, you signed up for the course. So yes, you are ready to. Now, before we do, let's talk about notation. All of these things are different ways of writing the derivative. F prime of x is the way we say it. It means the derivative of f of x. dy dx means the derivative of the function y. Notice how it works here. The notation, different notations, you use the one that makes the most sense at the time, and you'll see as we go through the year why one makes more sense than another sometimes. Most of the time doesn't matter. That second one, though, means the derivative of the function called y with respect to x. It's indicating to you that the variable is x. If the variable was t, we'd have dy dt. For the first notation, if the variable was t, we'd have f prime of t. Okay? So the notation should do a couple of things for you. It should give you what the function's being called, either y or f, and what the variable is. X, usually. T will run into some r. Okay? Now this next one, y prime, doesn't tell you what the variable is. It tells you the function's being called y, but it doesn't tell you what the variable is. Therefore, even though it's a really nice short notation, sometimes it's not as useful because it doesn't tell you what the variable is. Because what if you're working a fairly complicated problem near the end of the year where you have the rate of change of a rate of change and you have y's and x's and t's? That one doesn't tell you which one you found the derivative with respect to. So sometimes that's not a good notation. Most of the time it's perfectly fine. The next one, that means the derivative of f of x with respect to x. So the function's called f of x. Its derivative is with respect to x. In other words, the variable is x. Well, better be if we're calling it f of x, hadn't it? All right. It could be the derivative of f of t with respect to t. Okay. And this last one is the least used. It means the derivative of y with respect to x. It's pretty straightforward. It's just not used all that often. Okay? All right. And see the different notations. You can do the limit as delta x approaches 0 of delta y over delta x. I'm not real fond of that. I prefer that because it means the same thing. Because the way you find the change in a variable is to subtract where it ends. Well, start where it ends, subtract where it began. That tells you how much it changed, right? If it started at 5 and ended up at 9, 9 minus 5 tells you how much that variable changed. So you might as well just write it out the way it is. All right. Now, calculus being calculus, it's not good enough to have one definition of the derivative. We need an alternative definition of derivative. So this is on page 101. F prime of C. Now, this alternative form of the derivative, f prime of C. C is not a variable. Okay, C is a number. So this form of the derivative gives you an actual number when you're finished as opposed to a formula. The definition of derivative, this one, is a formula to find the slope of the tangent line. When we do some of these here in a few minutes, you'll see that we usually end up with x in our answer. So it's a formula to find the slope of the tangent line, and you can use that formula at any point on the graph of f that you want to. What the alternative form does is instead of giving you a formula to use at any point you want to, gives you the final answer for the slope of a tangent line at a certain point. If you want the derivative at another point, you got to start over and do the whole process again. So the alternative form has its use. If you know for a fact you only need to know the slope of the tangent line at one point, it's perfectly fine. If, on the other hand, you know that you need the slope of the tangent line at 7 points, this is no good because you have to work the problem out 7 different times to get 7 different answers, whereas when you use the definition, that gives you a formula. Then all you got to do to get your 7 different slopes at 7 different points is stick the x-coordinate in, and it takes 2 steps. Okay? But we will use the alternative form of derivative, and when we need it, it's very useful. Okay? One place it's useful is this. If we have this kind of thing going on, we can't find a limit as x approaches, or we can't find a limit on both sides of that point right there. But we could find the limit from the right. We can't find the limit both sides there, but we could find the limit from the left. And so the alternative form is very useful when that kind of thing happens. Okay? So that's the alternative form. Know it, love it. Do you all have it written down? Write it down. All right. Now, we have a theorem at the top of page 103 that says if f is differentiable at x equals c, then f is continuous at x equals c. What it means is this. If you're able to find the derivative of a function at a certain point, that the function must be continuous at that certain point. And think back to the logic we did in geometry a few years ago. Converses are not always true, are they? If a function is differentiable, differentiable means that you can find its derivative. If a function is differentiable, then you can conclude it's continuous as well. The converse is not true. If a function is continuous, that does not necessarily mean that it's differentiable. I don't want to give you an example of that right this minute. Just remember it when we come back to it later. If the function is differentiable, conclude that it's continuous. If it's continuous, don't conclude that it's differentiable. All right, now, you need to put this down in your notes. The derivative of a function is a formula to find the, and then there are three things. The derivative of a function is a formula to find the slope of a tangent line to that function. The derivative of a function is also a formula to find the rate of change of that function. And if the function gives you the position of a moving object, then the derivative is a formula to find the velocity of that object. Yes?
So, why is it important to find the slope of a tangent line?
Because the slope of the tangent line, which is what we worked with to get the definition, slope is rate of change. That's really what we're after. Rate of change is really what we're after. Like back when all you knew how to graph was a line. If the slope of that line is 2/3, then the rate of change of whatever that data might represent is 2/3. Okay? Just the rate of change. If you've got a moving object, the reason this turns out to be velocity as well, you know, if that's position and that's time, and, you know, you went 100 miles in 1 hour, the rate of change, the slope of that line would be 100 over 1. So it'd be, I did that backwards, didn't I? I did it upside down. Should be 100 here, 1 here, okay? Then the slope would be 100 over 1, which is the rate of change, 100 miles per hour. That's the velocity. So all these three things, you can't have one without the other. The generic term is rate of change. But when it's a moving object, we'd rather call it velocity. That's a more specific term. And when it's just something that we've graphed, we'd rather call it slope, because it's easier to think of slope than it is to think of rate of change. But they're all three the same thing. This being really what we were after. Because if you can find the rate of change, you've also found the slope and the velocity. But, you know, I'll list it in this order because slope's the one that's easier for us to understand. Does that help at all? All right. Now, here's the cool thing. Because before we had to do lines, right, to find slopes. Well, now that we know the derivative, we can find the rate of change of that function anywhere we want. Because look, the rate of change isn't the same everywhere, is it? Because it's not changing very quickly down here at all. But then when we get over here, the rate of change, that's a really steep slope. It's changing. Whatever it is we measured is changing very quickly. So, yeah, I mean, it might be exponential. Who knows, right? So that's why now all of a sudden this is pretty cool, because we couldn't measure the rate of change of objects before unless when we graphed them it was linear. But now we can. So if you think back to the very first calculus lesson we did where you had to tell if calculus was required to work a problem, we couldn't have found the rate of change of that kind of a graph before, but once we get good at derivatives, we can. And that might be, I mean, it might be important. It depends on what you're doing with it, but it could be really important. If you're measuring, you know, the growth of, you know, cancer cells, that equal bad, right? You'd much rather it be like this So the rate of change of things can be really important sometimes. Once you have the formula for the slope of the tangent line, the rate of change, velocity, then you can find the slope or the rate of change or the velocity at any point you want. Okay? Usually we only want to do this at 1 or 2 points. But again, if that graph really was measuring the growth of cancer cells, we'd want to find the rate of change at a lot of different places because we'd want to figure out why this is happening, right? So we would want to find it at a lot of different places. So that's why the definition of derivative is really more useful than that alternative form. The alternative form is fine if you only need to know the rate of change at one particular place. But otherwise, you would like to do the definition of derivative and find it wherever you want, as many times as you want. Now, since the derivative is a limit, there is such a thing as a left-hand derivative and a right-hand derivative. The left-hand derivative would be the limit as delta x approaches 0 from the left. The right-hand derivative would be the limit as delta x approaches 0 from the right. Okay? Now, if the limit does not exist at a certain point, then the function is not differentiable at that point. Because we studied limits long enough to know that limits don't always exist, do they? We can have different things that happen to make a limit not exist. We can have the left-hand limit not equal the right-hand limit. We can have a vertical asymptote where the function's going to infinity or negative infinity or a different one from each side. Okay? Now, since our limit is the slope of a tangent line, here's where this differentiable and continuity comes into play. We said that if the function is differentiable, you can conclude that it's continuous, but not the converse of that. Because if you have a function, I don't have a good picture of it here first. If you have a function that does this, has that really sharp point on it there, that's called a cusp or a sharp turn. Okay? That function is not differentiable there. Because think about how many different tangent lines you could draw through that point right at the end. You could draw that. That could be a tangent line. And that. Or that. Yeah, so what that means is at that one little point right there, whatever that C is, it's not differentiable because there's not a slope of the tangent line. That's right. Okay? So anything, well, so I'll read what I wrote here. Thus, a function is not differentiable when its graph has a cusp, a sharp turn, or, you know, the function doesn't exist there for some reason. There's a vertical tangent line. It's discontinuous. There's a hole in the graph. The ends don't meet. You know, whatever could happen there. So, like when we discussed continuity, even functions that had a lot of discontinuity were continuous a lot of places as well. Even functions that are not differentiable at certain places are differentiable at a lot of other places. So if you look at this first graph, this step function, this greatest integer function, this function is not differentiable at every integer because it's discontinuous at every integer. The limit from the left wouldn't equal the limit from the right. Okay? If you have an absolute value function, this right there at 2 would qualify as a cusp. There's a lot of different tangent lines I can draw through there. So the limit there would not exist. Okay? Look at it this way even. What's the slope of that part of the graph? 1. So what's the derivative equal for all of that part of the graph? 1. Because the derivative is the slope. In this weird too, lines are their own tangent lines. Anybody's brain just explode? The graph of a line is its own tangent line. Ooh, we define it that way. So it works. Those are good questions. And sometimes in math you have to define things to make sure that they work. Okay? But look, what's the slope of this part of the graph? -1. So the right-hand derivative would equal +1. The left-hand derivative would equal -1. Since the left-hand and the right-hand derivative don't equal each other, guess what that means? The derivative does not exist. Following how limits and derivatives work together? Why do derivatives and limits work together like that? That's right, because of the way we define derivative. The derivative is a limit. So that means then that all of the things that happen with limits have to happen with derivatives. You can have places where limits do not exist. That means you can have places where derivatives do not exist. Okay? This one's fun here too. At x equals 0, and normally we don't like tangent lines to cross the graph, do we? Because that seems like it's cheating because, you know, you could put tangent lines everywhere like that. But here, to have a line that only intersects that graph at one point, it does have to cross it. It has to be vertical. Whereas like out here, you don't have to cross the graph to get a line that intersects it at just one point. Okay? But what's the slope of a vertical line? It's undefined. So if we tried to find the slope using the derivative to find the slope, we would get undefined. And when a limit turns out to be undefined, we say that it does not exist. So the derivative does not exist at x equals 0. Not differentiable is the same thing as saying the derivative does not exist. I don't know. I'll have to think about that. I'll look that up. Okay? Let's do some problems. Again, you guys signed up for the course. All right, I'm on page 104. In exercises 5 through 10, find the slope of the tangent line to the graph of the function at the given point. All right. For number 7, g of x equals x squared minus 4, and the point they give us is 1, -3. So the slope of the tangent line equals the limit as delta x approaches 0 of f of c plus delta x minus f of c over delta x. Let me skip this part for a minute. Let me show you the best way to work this problem first. Let's do this. The derivative is a formula to find the slope of the tangent line. All right, so that's the definition of derivative, isn't it? So let's use that because I've told you that the derivative is a formula to find the slope of the tangent line. So let's use this as a formula to find the slope of the tangent line. Now, g of x is given to us to equal x squared minus 4. Now, our definition says f. Okay, so they called it g this time. Who cares, right? Just change, don't actually change it, but if I change those to g's, I'm back in business for calling this one g, okay? All right, so the first thing I want is f of x plus delta x, or g of x plus delta x. Remember how it works. Whatever's inside the parentheses, that's what you substitute in for x. So if x plus delta x is inside the parentheses, that's what I substitute in for x. So instead of it being x squared minus 4, it's x plus delta x squared minus 4. We struggle with this sometimes. Do you follow me? Yep. For instance, if that had been f of 3 in the definition, then since that's our function, we'd put a 3 in there. Okay? Since it was f of x plus delta x, we put an x plus delta x in right there. So, what I've got underlined in red, that's f of x plus delta x. Minus means minus f of x. So just write down the definition of your function, x squared minus 4. Put it in a parentheses. Why am I putting it in a parentheses? Because I got to distribute the negative. Otherwise, I'm not subtracting all of it, am I? Everybody with me? And what's our denominator? Delta x. So let's pause for a moment. Questions? All right. Now we're back to chapter 1. Find the limit. We can't substitute because that would give us a denominator of 0. So we need to try some algebra, don't we? We need to square that one parentheses. We need to distribute that negative. Then hopefully some like terms will combine and the magic will occur and it'll work out just right. Let's see if it does. First, let's square that binomial. If you have a plus b and you square it, you get a squared plus 2ab plus b squared. So when we square that, we'll get the first term squared, that's x squared, plus 2 times the first term times the second term, so 2 times x times delta x, plus the second term squared, so delta x squared. So that became that. Don't forget to copy down the minus 4. And then on that last parentheses, we need to distribute the negative, don't we? Negative x squared, positive 4. All right, are some good things getting ready to happen? Yeah, they are actually. Because positive x squared and negative x squared give us a 0. Negative 4 and positive 4 give us a 0. So now we're down to the limit as delta x approaches 0 of 2x times delta x plus delta x squared over delta x. Factor out of delta x. Because when I factor out of delta x, I now have the limit as delta x approaches 0 of. Well, when I take a delta x out of 2x delta x, I'm left with a 2x. When I take a delta x out of delta x squared, I'm left with a delta x.
Miss Adams and Scott Turner's homeroom, the gym, please, for pictures.
Everybody with me on the factoring? You ready for a woohoo? Because I can divide those common factors out. So now I've got the limit as delta x approaches 0 of 2x plus delta x. Can I now substitute 0 for delta x? Yes. So f prime of x equals 2x. That's our formula to find the slope of the tangent line. If we want the slope of the tangent line at the point where the x-coordinate's -4, we just put a -4 in for x. If we want the slope of the tangent line where the x-coordinate is 2/3, we put 2/3 in for x. The point they gave us was 1, -3. So to get the slope at this particular point, what do we put in for x? 1, the x-coordinate. I mean, duh, don't put the y-coordinate in for x. Kind of defeats the purpose of calling them different things. So the slope of the tangent line at that particular point is 2. And notice the notation. I called it f prime of 1. F prime of 1 means the value of the derivative when x equals 1. Is that awesome or is that awesome? Hey, you did real calculus just then. Real, honest to goodness calculus. Not stuff to get you ready for calculus. Calculus. All right, and now for the bad news. Oh, come on. There's got to be bad news. All right. That's a fairly simple function, isn't it? And that was the easy way to work this one. And it still took a few steps. Yeah. Think how much fun it's going to be when you have, throw a little trig in there and some square roots and some x to the, hey, how about an x to the 7th? So that when you substitute f of x plus delta x, it becomes an x plus delta x to the 7th? Those are good times. Yeah. All right. We've got 10 minutes. Maybe we can finish this problem. Let's see. Now, the way I skipped at the beginning was to use the definition of the slope of the tangent line instead of the definition of derivative. Now, the book's version of the definition of the slope of the tangent line has a c here and a c here instead of an x, like the definition of derivative has. So, instead of working this with the variable of x, work it with 1 in there for c. Because that's what c stands for, the x-coordinate of the point of tangency. All right? C stands for the x-coordinate of the point of tangency. So instead of a C, put the x-coordinate of the point of tangency in there. So put a 1 in there. So the slope of the tangent line would equal the limit as delta x approaches 0 of f of 1 plus delta x minus f of 1 over delta x. Now, again, this is our function. So when we find f of 1 plus delta x, replace the x with 1 plus delta x. Okay? The limit as delta x approaches 0. The two things I underlined in red are the same thing, aren't they? The second version is simply, I replaced x with 1 plus delta x. You with me on what I've got underlined? All right. Right. It's exactly the same as the first. Instead of x as a variable, we have 1. So in effect, we have no variable other than the delta x. So instead of getting a formula, what are we going to get as our answer? We're going to get it for just that point, aren't we? This is using the definition of the slope of the tangent line instead of the definition of derivative. Then be careful on the rest of it. Minus sign, parentheses, f of 1 means put a 1 in for x. So 1 squared minus 4 over delta x. So that's the limit as delta x approaches 0. Then again, when you square a binomial, you'll get the first term squared plus 2 times the first term times the second term plus the second term squared. Don't forget to copy down that minus 4. And then look, I saved us a whole step because in that parentheses, 1 squared minus 4, that's a negative 3. And then I distributed that negative, make it a positive 3. Now you didn't miss everything, just the important stuff. Yeah, we are. Everybody with me? All right, now look. What's negative 4 plus 3? Negative 1. What's negative 1 plus 1? Not 2. 0. So all the constants are gone. Once I get to this step, now what do I need to do? Factor out the delta x. So I have the limit as delta x approaches 0 still. Now that I've factored out the delta x, I'm going to divide out the common factor. Now I can substitute, and now I know what the slope of the tangent line is at that particular point. Right. Now, you see why the definition of derivative is more useful than just the definition of the slope of the tangent line. Because this took just as long, and it was only useful for that particular point. If we changed and decided, oh, crud, that's not the point I needed to know. I needed the point to whatever. You'd have to just start over, wouldn't you? You have no choice. You'd start completely over. Whereas, if you use the definition of derivative, and you've got this formula, you're like, oh, I didn't want to use x equals 1. I want to use x equals 2. Takes you 5 more seconds of work instead of 5 more minutes of work.
So why would we use the other formula?
Mostly because it's there, and we would rarely want to do it that way. Okay?
So essentially, if you can't use it, it'd be easier. Or
It's possible, depending upon what the function looks like, that doing this is worth the effort. Just to, it's not likely, but it might be worth the effort if the doing it the other way is just too cumbersome. But 99 times out of 100, I'm going with this. All right, now, there's another way to work this. It's with the alternative form of the derivative. See, you thought having 2 methods was bad. We have 3 methods. So it's the same problem. This is the alternative definition of derivative. Alex will show you. So, the alternative definition of derivative is f prime of c equals the limit as x approaches c of f of x minus f of c over x minus c. Since the point they wanted us to use was 1, -3, c stands for the x-coordinate of the point of tangency. So every place you see a c, replace it with a 1. So, there, and there. You replace the C with a 1. Why with a 1? Because 1 is the x-coordinate of the point of tangency.
Whoa.
And see if you can work your way through that for your homework.